Okay, let's get started. The agenda for today is to summarize what we had on the board about homomorphisms, add one small little bit, go over the homework, and then introduce isomorphisms. So, to summarize, first, so a map from the group G to the group H, the homomorphism if I apply the operation to the product in G of two elements, I get what?
G1 star G2.
Good. I get the product in H of the two results, right? So those are two completely different groups, and they could even have completely different operations, as we saw by one example anyway. So that's the definition. And then it has three big properties, right? Every homomorphism shares if I apply the map to the identity in G, I get the identity in H, right? That's property 1. If I apply the map to the inverse of G, no. What do I get? I get the inverse of its image, right? That is, if phi of G gives me the element H, then phi applied to G inverse gives me H inverse. But these two together mean that the image of the entire group under the map, because it maps from G to H, every answer is in H, but because the identity goes over and inverses are preserved, we obviously have closure because every image lives in H. Phi of G is a subgroup of H. It's called the image in G under the homomorphism. And it's only because it's a homomorphism that is a group. Otherwise, it would just be the range of the function. And then we have a third property, that order is kind of preserved. In the sense, if the order of the element G is n, and I'll use the same notation, H being the image, then we know that also H to the n is the identity in H. That is the image of G to the n is H, but that doesn't mean that the order of this element is n. What does it mean? If H to the n is the identity, what do I know about the order of H? It could be n, but
it divides n.
Yeah, instead. Yes. For example, it could be that the image is the identity, right? And the identity is 1, right? All I know is the order is some divisor. Yeah. Okay, so that's what we had on the board. Those are the basic properties of a homomorphism. And we established that the image is a subgroup. I want to establish now that another important subgroup that is derived from the fact they have a homomorphism. And we define the kernel of any map to be the set of all elements in the domain that give the identity in the codomain as the answer. We know, for example, because this is a homomorphism, that this set isn't empty. What's one element that's guaranteed to be in there? What's one element that's guaranteed to map to the identity? The identity of G. So I know that always the identity in G is an element of the kernel. That the kernel, in any case, is a subgroup. Well, this is step one, right? The identity's in here, always. What else do I need to prove that this thing is a subgroup of G? Closure. So, good. So how do I prove closure? Suppose that G1 and G2 are in the kernel. Wait for the jets to disappear. Okay. G1, G2 are in the kernel, then I know automatically that phi of G1 star G2, because it's a homomorphism, is what? It's the product of the images of those two elements, right? Maybe they decided to shut down Washington in mysterious ways. They're not that far away. Okay, but these two elements are in the kernel, so what are both of these results? The identity of H, right? The identity operated with the identity is, of course, the identity. But what does that mean if phi of this product is the identity? What can we say about this element? It's in the kernel. That's closure, right? If I take any two elements in the kernel and I operate on them, I get another element in the kernel because the image of the product is also the identity. So I have the identities in there. I have closure. What else do I need to be a subgroup? Inverses. Inverses. So how do I prove that inverses are in there? Well, suppose that G is in the kernel. What's my job to finish this stuff? What do I need to show?
The inverse of G?
The G inverse is in there. Then phi of G inverse, because it's a homomorphism, is what?
Phi of G.
It's the inverse of phi of G, right? Is the... But G's in the kernel, so what is phi of G? G's in the kernel, so what's phi of G? The identity. So this thing is equal to EH inverse. What's the inverse of the identity? The identity. Therefore what? Therefore G inverse is in the kernel. Because when I apply the map to G inverse, I get the identity. Therefore, and that's the most important part of the proof. Don't just do the arithmetic. Write down the answer. Write down the conclusion. Therefore, G inverse is in the kernel. And so now I get the nice conclusion. And notice how I used these important properties that I had to show first. I used every one of them. Well, except for the order. I used those first two. So the conclusion of the fact that the identity is in the kernel is closed, and it has inverses, therefore the kernel of any homomorphism is a subgroup. Of what? G, because notice they're all parts of G. Okay, let's do an example of this one. That should be familiar to you. Let that settle for a second. So, hint, hint. You should be able to prove that something is a subgroup. That's why I put it into it, right? It's always reviewing because we're always building on the stuff we've done before. So let's do an example of a map where the kernel is a subgroup. Consider. Linear transformation, I'm going to leave it as with a square matrix representation from Rn to Rn, where T of x is Ax. Remember, the vector space Rn is a group under what operation? Rn is a group under what operation? What do I do with vectors? I get another vector.
Multiply.
How do you multiply vectors? You add them, right? This is a group under vector addition. So both of these are groups. So what would be the kernel of T by my definition? It's the set of all elements in Rn such that what? By definition of the kernel. Well, what's the identity in a vector in a regular old vector space? What vector is the identity for addition? The zero vector, right? Such that T of x is the zero vector. But remember, every linear transformation has a matrix representation. So this is the same thing as the set of all, well, common symbolism here. The set of all x in my vector space such that Ax equals the zero vector, and that set of vectors has another name with respect to that matrix. What is the set of all vectors that give me zero when I multiply by a matrix called? The null space, right? This is equal to the null space of A. All right, well, let's prove that that really is a subgroup of Rn. Well, first, let's do it the hard way, then let's do it the real easy way. To prove it's a subgroup, I need to look at three things. Identity, T of the identity is A times the zero vector, which gives me, I multiply the matrix times the zero vector. I get the zero vector. Therefore, zero, the zero vector, is an element of the kernel.
How did you know to use the zero vector?
Because it's the identity. Right? If I add the zero vector to any vector, right, that's the identity in Rn. We're doing vector addition, so the zero vector is the identity. Good question. So 0 is an element of the kernel. So we have identity. What else do I have to show for subgroup? Inverse. Inverses. Suppose P of x equals 0. What's the inverse of x, of the vector x, in here? Vector addition. So what's the inverse? Negative x, right? Then t of minus x is the same as t of minus 1 times x, right? But that's the same as a times minus 1 times x, right? Minus 1 is a constant. What can I do with constants in matrix multiplication? Pull it out, right? So that's the same as minus 1 times ax. But what's ax? It's 0. Zero vector, right? This is zero vector. Therefore, I have inverses. So I have inverses. Or, in other words, if x is in the null space of the matrix, and so is minus x. What else do I need? Closure, right? I want to prove it's a subgroup directly. Closure is number 3 we need to prove. So what do I assume to prove closure? What do I need to assume to prove closure? Yeah, or in this case, assume x1, or let's use two vectors u and v. Assume the vectors u and v are in the kernel of the transform. Then I want to look at what to prove closure. The transform applied to what? What's the operation? Addition, vector addition. Then I want to look at t of u plus v. Well, that by definition is a times the vector sum u plus v. But according to the rules of matrix arithmetic, what can I do with that a?
Distribute.
Distribute. That's the same as au plus av. But where do u and v live? In the kernel, right? So what's a times u? The zero vector. V is also in the kernel, so that's also the zero vector, and that's the zero vector. So we have closure. So the big therefore is we've proven that the kernel of this linear transform which is the null space of the matrix, is a group. So that's the big therefore. Ker T equals null A is a subgroup. Rn as a vector space. It turns out it's actually a subspace too, but we don't worry about that in this case. But this was way too much work. Way too much work. What did I just prove before we started with this example? I proved that the kernel of any homomorphism is a subgroup. Right? So all I really need to show is that this map is a homomorphism. So how do I prove homomorphism? I consider T of U plus V. Right? If it's a homomorphism, what must that equal? It must equal T of U plus T of V. So that's A times U plus V, which by distribution of matrix multiplication maps AU plus AV, but that's equal to T of U plus T of V. Therefore, T is a homomorphism. That's the easy way. Therefore, Ker T is a subgroup. By the previous theorem. That's why we do theorems, right? To save work. That's a whole lot easier than proving subgroups step by step. Once I establish that any particular map is a homomorphism, the range is a subgroup of the codomain, and the kernel is a subgroup of the domain. That's a nice property to work with. Okay, I think we can kill the tape here.